Hello. I present myself again. So I'm Salvatore Marino. I'm from the Budapest Technical University. I want to talk about pseudo-ductility, which is specific behavior of composites. This was previously introduced by Yantel in his presentation, and now I want to make an overview of the state of art of this particular feature of composite. I will call it in this way. I want to introduce composites in a very general way and talk about hybrid composites. I will be very specific talking about this pseudo-ductility because it's a very wide topic. It also involves composites even in a civil engineering aspect. So I will focus more on this hybrid composites, especially for made by fiber reinforced composites. So I want to make this clear from the beginning. And so the state of art of the approach, the successful approaches, the literature reported so far, and the new approaches, which are more related to results we collected at the Budapest University. What are composites? Everybody knows this. It's obvious things to say, but let's remark it. It's made by fibers together with matrix. And why they are so interesting is because they are outstanding material with excellent mechanical properties. And we like them because they have a high strength to weight ratio. And this makes them more desirable in comparison to metals, and especially for high performance applications. For example, the aircraft industry, they are quite attractive. What's the problem with composites? They present brittle behavior after a linear elastic behavior. They fail catastrophically. And this is of course an issue from the safety point of view. So there is no safety margin before the final failure, something that tells us that this material is going to fail, and let's do something to avoid it. So sometimes this failure could be unexpected. What's one of the biggest issue with composites that is common in the composites, since they are made by combination of plies that create this laminate, the laminates can debond each other and for delamination, the lamination could compromise seriously the load bearing ability of the material. So based on these two main problems related to composite, what we need to have is, for sure, from the safety point of view, which is one of the most important, we need a kind of safety margin before the final failure. We need to know when composites is going to fail, when we have an overload, when the composite's no longer able to carry the load because it was damaged inside and it's not possible to see with naked eyes. And we also need to find a way to suppress the lamination. But the lamination point of view is more clear towards the end of the last part of the presentation, which is more related to approach we do in Budapest. So to provide this safety margin, one of the most common approach is to hybridize composites, to create a kind of multi-stage damage process. In this case, Yantel, of course, introduced hybrid composites very well. And just to summarize these materials, they are mainly made, most common composites are made by glass and carbon. And they give us this combination of behavior, which is an average behavior between the low elongation material and the high elongation materials. There are different ways of hybridizations. They could be summarized here with this kind of layouts. We have interlayer hybridization, intralayer, and intra-throw hybridizations. And all of them are good solution for generating pseudo-ductility in hybrid composites. As I said, we are interested to create this multi-stage. First of all, this is necessary to see, okay, we overcome this linear stage, this initial stage. We are in this stage that could show us different scenarios it could be unstable or stable. This depends, highly depends on how hybrid composites are designed. And with this stage, we are able to see that some damage is occurring inside composites, and before approaching the so-called final stage, which is where the composites after some extra interval of strain is going to fail. Also, hybridization is, let's say, one of the most effective ways to achieve pseudo-ductility, and now I'm going to show you why. Let's define what is pseudo-ductility and why pseudo. So, of course, everybody knows the ductility definition, which is more related is exclusively related to metals, and which is the ability of the material to yield and keep some permanent deformation. But the fact in the metals is that when metals are unloaded, they go back to the zero load level, and they come back are reloaded with the same elastic modulus. In composites, this doesn't happen, but this combination of pseudo-ductility is because we have damage, so we have still a brittle behavior inside. So the feature of composites is they are still shows fractures inside and high strength. And the ductile behavior is that we can extend the deformation of composites up to a high value of elongation. Different approach of hybridization could create different good grades of pseudo-ductility. Here we see a schematics of how many different hybridization approaches generates anyway pseudo-ductility. And this approaches, the hybridization, it's good because it separates the fracture process. So isolate the low elongation fibers together with the high elongation fibers and isolate the fracture process. And it's one of the base concept to generate this plateau stage that progressively, and this is stepwise, until the final failure of the material. Hybridization is not the only one. I will focus more in hybridization in the next slides. There are other approaches as well, and one of them is a very, let's say, clever design of material, which exploit the angle ply design of composites. There are composites with a stacking sequence with different angles, each other, and pulling under tensile load. Let's consider this case, the rotation of the fibers. And rotation of the fibers give us the possibility to create this transition, this stable transition. This configuration is also could be considered is like in the borderline, because it could be considered also ductile. Also, the authors, Jonathan Fuller, was leading this research, and the authors called this ductile material because with this loading and reloading test, they have seen that what I said at the beginning, what was the definition of ductility for metals, that the elastic modulus at the beginning was exactly what was the same. So it was kind of provocative definition of achieving ductility in composites. In fact, they use this kind of double keywords in the research. Short fibers, and now we are in the hybrid composites category. So short fibers are one of the most easy way to achieve pseudo-ductility, because in this case the fracture process is based on the gradual fracture of the short fibers. So the pull out of the short fibers and they fracture generate the different grade of pseudo-ductility. This trend depends on the grade of the hybridization. In fact, I want to highlight how the initial stiffness of the material increased as soon as we increase the content of the carbon. So more carbon, of course, since the carbon is stiffer than the glass, increase the initial stiffness, and the short fibers can let us to exploit the potential of the carbon, of the stiffness of the carbon, which is very important, because with hybridization we can lose some performance of the carbon layer. But in this case, we can play a little bit with this kind of grade of hybridization and try to exploit as much as we can the potential of the carbon and still have a pseudo-ductile effect. The only issue with this configuration is that quite challenging to create the layup and align the fibers. There is a method, it's coming from a research program, HyFiSyn, and they invented this technology where short fibers are mixed in a water solution. They are put on a kind of grid, and they are dried. And using this kind of plates, vertical plates, and some vibrations, the short fibers are aligned each other. And this is very good also for using recycled fibers. There are research papers that show that also this pseudo-ductility was achieved even employing recycled fibers in the layup, which is very good considering the issues we have in recycling composite materials. Another strategy for generating pseudo-ductility is not based on the fracture of the material, the fibers, but on the delamination. So strategically creating a layup and designing the layup that give us the possibility to gradually delaminate the material. In this case, the configuration is called brick and mortar. It's possible to also generate this kind of deviation. The approaches for pseudo-ductility based on delamination allow us to generate this very smooth transition. Could be that it's a little bit harder to generate with fragmentation or fracture of the material. As of course, this depends on how well is designed the material, but thinner is the carbon. I will talk about this later about the fragmentation, but it's in other approach, this smooth transition, it's not that easy to find as well as in the delamination in the delamination based pseudo-ductility. A further step on this approach in this strategy is to exploit the carbon epoxy platelets. So creating an interply hybridization. So we have a kind of sandwich where the external plies are the glass layers. The middle we have this continuous layer of carbon. The carbon is pre-cut. So we have this discontinuities, and among this is to trigger delamination. In fact, in a tensile test, we see that delamination start propagating from the cuts, and it's continue. And as soon as this strain interval ends, it gets a kind of saturation. So. And at the end, and in the last stage, we have the pull out of the glass solely. I wanted to say something, but I forgot. Anyway, yeah, the problem is with this, exactly, I was looking for this formula, sorry, is that we cannot create cuts as much as we want. And of course, denser is the presence of the cuts, better is the pseudo-ductile behavior. But of course, we reduce the initial stiffness of the material because we reduce the potential of the carbon, the contribution of the carbon to the initial stiffness of the hybrid material. So we need to find a trade-off to what is the level of the pseudo-ductility we want to achieve with the initial stiffness as well. And here comes with the fragmentation. Fragmentation is one of the most common approach used. It relies on the use of thin plies. Thin plies, they are very good in suppressing the laminations. They have a low energy, they fracture, they release a low energy, they fracture, and the fragmentation here perfectly visible, because hybrid composites also have this kind of special feature, the translucency of the glass allow us to see what's going on inside. So how the material or the laminate or fragment, so we can see the damage, and that could be also useful for having a safe material as well. But in this case, the fragmentation requires that the central layer, the low elongation material, which in this case is the carbon one, start to fracture, and it forms multiple fracture together with increasing load. Most of you most probably know this map is called the damage mode map, and it explains clearly that to achieve the fragmentation of the material, we need a strict rule about the designing of the hybrid material. And first of all, as you can see, in the vertical and horizontal axis, one of the common parameters is the thickness of the central layer. So the carbon layer must be really thin, or at least it must be thinner in a way that as soon as it breaks, the energy released by the fracture should be lower than the fracture toughness at the interface of the material. With this study, we have 4 different scenarios. Actually, they are 3, because this could be considered in common. But this is the worst, of course, which is the premature failure of the glass. As soon as we have the fracture of the carbon, the glass fails as well. So the glass should be designed in a way that after the fracture of the carbon, we have enough strong layer of glass that carry the load. And that designing the glass in a proper way, it leads to this area. So as you can see, we are moving towards a thicker material in general, and that's could be considered an issue for practical point of view. But anyway, the delamination is created because, as I said, if we use a too thick carbon and it releases too much energy when it fractures, and the fracture toughness between the carbon and the glass is not enough to carry to absorb and suppress the lamination. So it's happened that we have a catastrophic delamination, which was similar to the video previously shown by Dr. Sell during the experimental activity. And this is the region we want to have. According to the design we have and the thickness of the carbon layer, so we want a thin carbon layer, and the thinner it is, the better is the fragmentation behavior. So we can suppress the lamination together with that. This condition summarizes perfectly what I want to say, what I said before, that the interface property counts a lot in the material. So not only the thickness, which is summarized in the formulas to generate the curves in the damage mode map, and the thickness, it's included in the alpha and beta parameters, which are the ratio of the thickness and the elastic modulus of the 2 materials. But this condition counts a lot too. The generation of the damage mode map, which by the way is a very useful tool for designing material, for designing hybrid composites, and especially if you want to have a pseudo-ductilities, is a parametric process where for each scenario we compare the lamination stress with the fragmentation stress, and if this fragmentation stress is higher than the lamination, is lower than the delamination, we get fragmentation instead of delamination. So it could be summarized in a flow chart, which is quite easy to understand. And but for the point of view of the fracture toughness, so as I said, the fragmentation-based pseudo-ductility is is easier to achieve when we employ thin plies. But using thin plies, we lose the possibility to have a high stiffness of the material at the beginning of the first stage. So as you can see here, I tried with some analytical predictions to change the thickness of the material, and of course, increasing the thickness of the glass, we lose the potential of the carbon, and of course that's not convenient at all. doing a parametric study in the damage mode map, just changing the fracture toughness of the material. So we are just keeping the same configurations, but acting on the interface and make it tougher. And tougher, it affects also, the toughness affect also the possible scenarios we may have. So if some configurations with the baseline material give us a certain value of fracture toughness, and we hypothesize to have 4 different configurations, these configurations are bad in any case with the damage modes. But if we increase the toughness, we may have fragmentation with some configuration, but how is the question? The approaches we recently implemented at BME were to act on the interface using a standard thickness carbon layer. This way we may have a good stiffness of the material at the beginning, but we want to use let's say energy absorption mechanisms, introduce some dissipation mechanisms that try to suppress the delamination and let the carbon to fragment. The approaches we tried were, first I want to show you this, it was made just introducing layers of epoxy films. In this case, we can say in other words, this approach is affecting the volume fraction of the material between the interface of the carbon and the glass layer. And introducing this extra resin and reducing this volume fraction, it gives us good results because this is the baseline with a very deep stress drop, because the material was not well designed for the pseudo-ductile point of view. In fact, we have the fracture of the carbon layer, stress drop, and then the final stage. In this case, the epoxy films contributed to reduce the stress drop, but some cases were also borderline. Let's say, in fact, these were borderlines, and a few cases were pure pseudo-ductile. But the outstanding results come from the nanofibers. They are capable to introduce crack deflection mechanisms or crack arresting mechanisms that can help us to suppress the lamination when the cracks start to wants to propagate between the interlayer, between the carbon and the glass. And putting the layer of the nanofibers and gave us a very nice transition, so very good pseudo-ductile behavior. Also, I want to highlight the practical aspect of this approach. This is not something that requires tricky treatment of the material. This nanofiber layer is like a paper towel, so it's like it's really easy to handle, and especially if the material is made by prepregs, so the stacking process, the manufacturing process is very easy to perform. So, and putting this nanofibrous layer is just like to apply it on the prepregs, put the rest of the glass plies on the top of it, and the material it's made. And the good thing is also that it doesn't affect the thickness, the final thickness of the material, because this layer will absorb the resin of the surrounding fiber reinforced layers, and it's kind of compressed. Of course, it's produced in autoclave, so with the 7 bar, but instead of using the resin film or the thermoplastic film, with this approach, we may keep the thickness of the material constant and do not affect the initial stiffness. Just to summarize the key facts about pseudo-ductility. Pseudo-ductility can be achieved mainly through hybridization. There are many approaches, but I would say that for high-performance material, for a high-performance structure, especially for aerospace or automotive industry, this hybridization, I think, is the most efficient way. And it's perfectly suitable for making hybrid composites safer. And also, I want to highlight the practical aspect of this approach. They are perfectly suitable for practical application and ready to be introduced in our industry. So that's it. Thank you very much.